In 2013, Boston Dynamics introduced the hydraulic atlas. In 2016, Hanson Robotics made its first robot, which they called Sophia. Sophia became the first robot to receive Saudi Arabian citizenship. Sophia was also the first robot to exhibit realistic facial expressions. In the big 2022 to 2024, Tesla unveiled Optimus, which focused on general-purpose labor. In the same year of 2024, Boston Dynamics retired its initial hydraulic atlas in favor of an all-electric model with superior dexterity. The manufacturing of a humanoid robot is a multi-stage industrial process. But before you get too excited, have you ever asked where these raw materials used for robotics are obtained? Are they mined naturally or developed artificially in the lab? Structural metals such as aluminum, titanium, iron, and magnesium obtained from Guinea, South Africa, Brazil, and Australia are used as lightweight alloys in the first stage of the making process. For electronic materials, lithium, cobalt, nickel, and manganese are extracted for high-density batteries, while praseodymium, silicon, and rare earth elements like dysprosium and neodymium, dominantly obtained from China, are processed as permanent magnets in motors. The Democratic Republic of Congo and Rwanda provide tantalum, which is processed into capacitors. Chips are processed from silicon, while gold is a circuit board connector. Germanium becomes infrared sensors and fiber optics, and gallium is an LED provider. Specialty and polymer materials are a big deal. That's why petroleum and natural gas are processed into high-performance engineering plastics like PEEK, polyamide, and polycarbonate for joint housings and internal gears. Material processing and refining comes in the second stage. Now get your eyes closer to the screen because it's time to sit and appreciate the art of robotics. Raw ores are not usable directly. They go through intensive processing. Now here's where heat comes in place during smelting and alloying. Iron ore becomes steel in blast furnaces when heated at a temperature of over 1500 degrees Celsius, and aluminum is extracted via the Bayer process from bauxite, then smelted using electrolysis. Still remember your chemistry? Why is electrolysis used in smelting aluminum? Because aluminum is highly reactive. To break its strong chemical bond with oxygen, electrolysis is the only feasible method to use. During the processing of rare earth metals, ore is separated through solvent extraction after being crushed and leached with acid. Sadly, this process has extremely polluting effects and is complex at the same time. Lithium refining. Over months, brine pumped from salt flats is evaporated in large ponds, then chemically refined into battery-grade lithium carbonate or hydroxide. Silicon, in its raw form, is purified to 99.99999%, that's a 9N grade for semiconductor use via the Siemens process. In the third phase of the process, component fabrication involves using refined materials at hand to produce subsystems. So what are robotic subsystems? Another point to put down, right? The frame, the structural skeleton, is formed by CNC machines and precision casting, usually aluminum or titanium alloy. All the parts are machined to micrometer tolerances. Some manufacturers, like Tesla and Optimus, use stamped aluminum for speed and cost. In every design, there's a yes, there's a no, and there's a wow, but in this system, there's a rather simple and critical part. Actuators. These are the limbs. This is the most critical and complex part of a humanoid robot. High-precision strain wave gears are paired with electric motors and sensors to create smart joints. Linear actuators convert rotational motion to push and pull for limb movement. Hydraulic actuators are used by cutting-edge robots like Boston Dynamics, requiring pumps, valves, and high-pressure fluid systems. Limb construction is done by attaching joints to structural links, arms and legs, and wiring them with complex internal harnesses. Torso and head. The central frame, which houses the main battery pack, cooling systems, and primary computer, is assembled. Full-body integration. Limbs are bolted to the torso, sensors and external skin or protective shells are added last. We have gotten a whole body. Now how is it going to move? That's why the brain is very important. We now proceed to computing and AI integration. Custom AI chips are fabricated at semiconductor factories like TSMC in Taiwan using photolithographic node processes. Remember the chips processed from silicon? They are bonded to substrates and encapsulated in epoxy before testing. Now this is the beautiful role copper plays through its printed circuit boards. The circuit boards are manufactured by laminating fiberglass with copper traces, drilled and populated with components via surface mount technology. What will these robots use as their window to the outside world? Do they or can they actually perceive smells? Let's quickly find out. Vision and speech systems. It's so incredible how RGB cameras, stereo depth cameras, and light detection and laser are used to give them not just sight, but in-depth vision. What about speech? How do they talk? Microphones are installed for voice interactions. Will this robot use a heart even though it doesn't have blood vessels? So how will it come alive? Yes, it will be given a heart, which is its power systems. Lithium polymers are assembled from individual cells, so cells are manufactured by coating metal foil with electrode slurry, drying, rolling, and packaging in pouches. Cell voltage, temperature, charge, and energy will be monitored by battery management systems, while power distribution boards regulate voltage to individual motors, computers, and sensors. Here's another tough component to build: the hands and end effectors. The hands require dozens of micro-actuators, tendons, and sensors. They may use tendon-driven systems, such as cables pulled by motors in the forearms. On the fingertips, soft robotics, such as soft molds embedded with sensors, are often used. For any design to be perfect, there must be an external touch of architectural finishing touches. That's why the outer shell is designed with rigid panels made from injection-molded ABS plastic or carbon fiber. To make it insane, silicon rubber is used to make a soft shell pigmented for a human-like appearance and embedded flexible electronics layers for distributed sensing. Now there's a head, there's a heart, and there's a skin, but there's no organization, so what happens from here? Stage 4 is the assembly, which takes place in a clean and climate-controlled factory room. Motors are integrated into joint modules. This is at the sub-assembly stage. Assembling of the skeleton is done by building the frame from the pelvic base, then the legs, arms, and head are attached subsequently. Motor gearbox units are mounted at each degree of freedom during actuator integration. Take this down. A full humanoid robot has over 50 degrees of freedom. That being done, thousands of wires and cables are routed through the body. This is one of the labor-intensive steps, and coming in is sensor integration, which involves precise mounting of light detection and laser, cameras, and inertial measurement units. Main compute boards and communication modules are installed before architectural finishing touches on the body shell are fitted. What do you call this body of work? Super or wow? Software loading and training. An amazing body alone is just lifeless without an operating system. After motor control and an operating system are installed, the robot is trained to learn balancing and walking, using reinforcement learning in physics simulators, followed by imitation, where it mirrors human movements recorded via VR. Algorithms like model predictive control are used to coordinate all joints simultaneously, while AI models are trained on massive data sets of human motion. This training is done repeatedly and in patterns in physics simulators like the Isaac Sim method, before being finally deployed to the real world. But before deployment, one more thing is very important to do. That takes us to the very final stage, testing and quality control. At this stage, dynamic calibration is done to test the zero moment point to ensure the robot can recover from an accidental push without falling. Cycle testing, moving the joints millions of times to ensure durability under heat and friction. Manipulation tests on the robot, like picking and placing, grasping of objects, and tool use, alongside stress endurance, and finally, the safety test, which involves forcing the robot's limits collision detection, and verifying emergency stop systems. So far, we have seen inside the factory, from raw material extraction to processing down to making a robot. How is it transported out of the factory? Transportation of a humanoid robot involves high risks of breakage, so manufacturers use unit load devices shipping protocols to move these units from factories to customers or research labs. Do you have any questions? Do you need more clarification about a particular area we explored? Please let me know in the comments section. Thanks for being with us throughout this process. If you are new to my channel, hit the subscribe button. Did you drop a like for this video? Thanks for watching. God bless you.